Thank you. It is a great pleasure to be here, and I'm really pleased to tell you about um, AI data readiness and what we have learned during the course of our AI accelerator here at MIT. All right, so I'm going to talk to you about AI data architecture and provide some of the definitions, obstacles, and best practices that we have learned over the past many years in helping many folks develop AI systems, world-class AI systems. So the bottom line up front is, as many of us know, there have been three main pillars to the AI revolution: data, compute, and software and algorithms. But for a given AI effort, these are often not all the same. In particular, it is often the case that the effort in getting data and making it AI ready is often 80% of the effort associated with an AI project. And the reason for this is quite simple. AI software is similar to other software with one big exception. In AI, data continuously writes the software. Thus, AI data readiness is often 80% of the effort. And so organizations that are world leaders in AI, they tend to bake in AI data readiness from the get-go. They don't ask themselves, are we going to be using AI in this data? They assume they're going to be using AI in this data. Now, the government has enormous collections of logs, but actually very little AI-ready data. And pivoting to an AI-ready data organization is a prerequisite for AI success. So that's just sort of the upfront message. If that's the only thing you get from my talk, then that's a pretty good message. And now I'm going to go into a little bit more detail on some of the definitions and give you some examples of making data AI ready. So again, why is AI ready data so important? It's because data drives breakthroughs in AI. And on this chart here, which you don't need to read the details of, but we have a number of breakthroughs in AI and the year they occurred. And then on the far right, you see kind of when the algorithms that led to those breakthroughs were first proposed. But then you look at when the data sets were first proposed, and you see there's a really big difference here. You can see that it's often, the algorithms often occurred decades before, but once the first really good AI-ready data sets appeared, the innovations happened quite quickly in a matter of years. And so this is a very important aspect and another reason why it's so important to make data AI ready. Now, when I talked to the previous chart and showed you about how much effort it was, I'm sure many of you are wondering, well, exactly where does this effort go? So I'm going to walk you through an example drawn from the cyber community where we made some data AI ready, and I'm kind of go through the details of that so you can kind of get a sense of where this effort goes. So what we want to do here is go from digital logs of cyber data or internet traffic data and making it an enriched AI-ready data set. Now, as I said before, logs are a ubiquitous output of digital systems, but their primary purpose is debugging. They're there to help people understand what's going on with the system. When there's an error, helping them track it down. The format tends to be very organic and highly specific to the digital system that was constructed. On the other hand, AI-ready data is scientifically collected data whose primary purpose is analysis. And the format typically is very well organized, generally comprehensible scientific tables. And so that's a pretty big difference. And so I'm going to walk you through what we did in this particular case, where we're going to take some internet dark space data and enrich it with some honey farm log data. So that's a set of computers that are engaging with services on the internet to learn more about them. And so we're going to take this data and make it enriched AI ready data. So here is just a few of the steps that we had. This is data from the CADA telescope, and I'm just going to walk you through these steps here from taking it from the raw form that as it comes off the telescope into the tabular data we need to do AI. So the first step, this is a very large data set. It's about close to 100 trillion packets, about 3 petabytes of compressed data sitting at the supercomputers funded by the Department of Energy at NERSC. And so we're very grateful to their assistance with that. So we have to first read all this data off of tape. We need to then decrypt it. It's encrypted. We need to decompress it. We then to select the various packets. We anonymize the sources, and then we save those anonymized data as traffic matrices, which we then can transfer to our supercomputer center here at MIT, the Massachusetts Green High Performance Computing Center. And again, it's about 300 terabytes of anonymized data. I want to say you can see that the data was really stored encrypted, and then we decrypt it, process it, and make it anonymized for subsequent analysis, because we have discovered that in this world, it's very, very important that we are always anonymizing our data whenever we can. And then finally, now that we have that data, we need to check, we need to calibrate and make sure the data makes sense. So what we can do is we basically grab some samples, in this case, 5 samples of about 1 billion packets each, taken from different times, and then we can plot the statistical distribution of the number of packets coming from each of the sources. And then we see here, when we plot it up, that the different times, they're very much consistent with each other, and they very much are consistent with sort of the standard heavy tail distribution that we would expect in this data. And it doesn't look anything like a typical light tail distribution like a Gaussian or a Poisson distribution, which we would not expect. And this looks really good, and the CADA telescope is one of the best sort of cited and best planned and calibrated data sets that we have access to. And so this plot looks really, really good. I will say that in many internet sensors, it doesn't look like this at all, and that indicates that you need to go back and look at where the sensor is placed and think about how you need to calibrate it in order to make something that is statistically consistent with what we would expect to see. So then that takes care of the raw data from the CADA telescope dark space. Now we're going to deal with our Gray Noise honey farm logs. And so Gray Noise is a company that collects this data. They do a very good job of it. And so we have a similar set of steps that we have to go through there. Obviously, we have to download and get the data. We then have to select the relevant fields. They collect a lot of data. It's in the form of JSON logs. So these are sort of log files that you keep a variety of fields in a sort of a hierarchical format. And we need to kind of go through each one of the fields and decide for what we want to do. Are we going to keep it, or are we going to discard it? You know, whether it's the core data associated with each source, the metadata associated with each source, the specific tags of the specific interactions that we see, the protocol that's used, and the ports that are used in the interaction. And so after we go through all this information, we can select the things that we want. We can then aggregate those in time. So we want to aggregate them in specific time windows. In this case, we aggregate them into monthly time windows. And then within each of those time windows, we then take all the data and aggregate by source. And we select the last time seen during that window, so we can have the latest record in that window. And then once again, we want to anonymize the data because that is sort of the conditions in which we are operating here. And throughout our analysis systems, we always assume we're working on anonymized data, and we've developed various methods that allow us to analyze anonymized data. And then we essentially save it as a simple tab separated value file. So now we have our two data sets, and we're ready to bring them together. So we have our CADA dark space data and our honey farm data. And then we basically have two distinct anonymized sensors. They're overlapping in time. They represent millions of sources. So here's just an example of the collections we have, the different months of the gray noise, our different samples of the CADA telescope data, and the number of sources there. And then we can basically cross-correlate. We've used the same anonymization scheme for the sources, so we can cross-correlate them and create our enriched data set by looking at common sources. And we see that there's a really large fraction of sources that are seen in both data sets, which allows us to build this enriched AI-ready data set. So now we have this data set, and you might think that we're done, but now we have to actually look at the collections of those and understand, do those make sense statistically? Is this good data? Is it properly collected? Does the correlations between them make sense? So we have about 10 columns of data here, several million rows. And the first thing we can do is look at the data set, the data from the two sources that were collected at the same time. And what we see here is if you look at the sort of the brightness of the source, how many packets were coming from the source, we can see over the different time windows, this shows the fraction of the sources in the CADA data that we're seeing in the gray noise data. And we see it follows it's very consistent, and it follows this sort of basic logarithmic curve here. And so this gives us confidence that we have a good statistical sample, that our sensors are well calibrated, and it gives us confidence that we could do AI on this data and not be overwhelmed by particularities of the sensor. So then we also want to check that this, if we just looked at the data that's collected at the same time, what happens if we look at data that's collected at different times? What does that look like? And once again, we see a fairly good, here the blue dots represent the data collected at different times compared to the CADA data, and we say it drops off rather quickly. It sort of decays over time in a very consistent manner, and we look at this across all the different data, and we see it has this sort of same behavior. So this, again, gives us a real confidence that this will be a useful data set to do further analysis on, that we don't have any systematic collection errors or calibration errors or citing errors that would cause this data to be not worthwhile. Again, I would say this is quite the exception, that most of the time when we collect cyber sensor data in the wild, it is filled with artifacts that require additional analysis and calibration. So this is a good case. This just shows the quality of the data coming from these two sensors. They work very, very hard to make that data this high quality. So hopefully this gives you a sense of kind of all the analysis you have to do, all the work you have to do, and gives you a sense of why it takes so much effort to get data AI ready. So moving on, one of the things I sort of emphasized here at every turn is that we want to create tabular data. Think about the kind of data that would appear in a scientific notebook with really well labeled rows and columns and units. Well, the reason for that is I've shown here kind of the core engine of modern AI, which is a neural network. So at the top, we have a classic neural network. We have input features. Each sort of column represents a different set of input features. In this case, I'm showing examples from imagery. So each column would represent a different image. And then several layers of the neural network. The lines represent the connections or weights between the various layers. And then for each image, we're going to have a bunch of output classifications. Each blue dot represents a specific category we can imagine. Here we're looking at faces, so you can imagine each one of these was potentially a different face. And the thing here down below we show is the deep neural network equation, right? This is this very simple equation that tells you how, when data comes in from one layer, how you manipulate it to pass it on to the next layer. And the key thing to note here is that all the values in blue are tabular data matrices. right? And so the reason we want our data to be tabular and in this format is because this is sort of what the system is designed to accept. And so that's why it's so important to get your data in a tabular format. So fortunately, tables are really a very natural format for data analysis. We've been using them as humans for thousands of years. Here's an example of a table from the 12th century. You can find examples that are a little less legible from thousands of years ago in cuneiform tablets. And we don't really even speak this language, and the numbers are Roman numerals, but we can still tell it's a table, right? In this case, it's a table of tides, but we can see that there's column labels and row labels and various numerical values. And so it is just very natural for human beings to look at this data in this tabular format. And this tabular data is compatible with nearly all analysis software, whether it be spreadsheets, databases. I've already talked about neural networks, various math libraries, and even within hierarchical formats like JSON and XML, you actually can still project them fairly easily into a tabular format. So this is a fairly good news story in terms of that, we need to get our raw logs into this tabular format. Fortunately, we have a tremendous number of tools that are available to do this. So at some level, people ask me, is this just spreadsheets? Well, pretty much, right? In a certain sense, here we have an example of a spreadsheet, and we see it shows, 4 completely different types of data. And it's really it's incredibly flexible, allows us to use a lot of very diverse data and put it in a common form. And I will include images. They are essentially a type of table, and other sort of sensor data is often organized in these tabular structures. They're used by 100 million people every day. And so I often say, people ask me, well, how do I know I have AI-ready data? It's like, well, if you can open up in a spreadsheet and it kind of makes sense, then that's probably a really good sign that you're well on your way to getting AI-ready data. So I've talked about kind of what AI-ready data looks like, and now let me talk about some of the obstacles. Why is it that this can be so hard to obtain? So, of course, the first thing, and this is particularly important in any organization, is that you can only use data that you're allowed to use. So you have to include data rights in your various agreements. So, on the left, we have the Apple iOS agreement, and on the right, we have the Google Android license. And you see that, the word data is mentioned many, many, many times in these agreements, because they're collecting data and they need to know that they have the rights to that data to do what they need to support their businesses. A second challenge, and this is probably one of the ones we run into most in government, is what we call SMEs versus ISOs. So subject matter experts versus information security officers. In almost any organization, sharing of AI data requires information security information security officer sign-off. These are the folks who basically say, yeah, I'm attesting that the release of this data is going to be more beneficial than any potential harm it might cause. Likewise, the advocate for that data is often a subject matter expert, someone who maybe knows something about the data or knows about AI, and they want to get the data released. Well, the subject matter experts and the ISOs have very, very different terminology. In particular, the ISO needs very basic questions answered, such as, what is the project? What is the need? Where will the data go? Who will be the personnel who will have the data? For how long? These are really, really basic questions, but subject matter experts often, in a desire to be helpful, will essentially send the ISO an entire research proposal describing what they're doing. And this really doesn't give the ISO a lot of confidence that the subject matter expert will properly handle the data. So one of the things we often do is sort of intercept this conversation and help coach subject matter experts in what the proper answers and handling of their information is, so that they can get through this process smoothly. And so I would say, a big issue is that if subject matter experts want to release data and get it in the hands of AI researchers who can do something with it, it's very important that they take the time to understand ISO terminology. It is not difficult, and it certainly would not be fair to ask ISOs to understand all the various terminology associated with all the different subjects that they would have to deal with. So this is a very important thing that we can do something about. So another thing that people often get confused by is development versus deployment. And these are almost always happening on two very different systems. It doesn't matter whether it's an industrial system or a defense system. You have here on the left, we see that we go from basic algorithm development, which is occurring in large data centers where we will do training on the data. We will build these AI models in the data centers. We then deploy them on a wide range of edge devices to do inference, to use the model to identify things in data. And then we will also collect additional data to further develop the algorithms and to test the algorithms and aggregate data back in the data centers. The exact same thing occurs in the DoD as well. And so a lot of times people get confused. There's a lot of vendors who will often try and sell people sort of one magical system that will do both of this. They're really very different. They're very different hardware. There's very different software used on different systems, very different types of people. The people developing algorithms are often very different than the people who would be good at deploying the system in the real world. So this is an important thing to emphasize and to understand, and it can cause a lot of confusion and really slow down AI data readiness. So finally, one of the things we have to be aware of, and I won't sort of walk through this equation here, is the various conflict of interest that exists in our cloud providers. Computing is phenomenally important in getting AI data ready, and the cloud providers and the cloud users often have very opposite incentives. In fact, there's very, very little incentive for cloud providers to lower the cloud bills of users. And so this can be a stressful and challenging situation as AI requires an awful lot of computing, an awful lot of data. You have to expend the cost to satisfy that. And so this can be a major barrier to being successful. I will say that as here in the AI Accelerator, we have our own supercomputers, and they have allowed us to execute the program at dramatically lower cost. Because we have those resources. So finally, let me get to some best practices and some various paths to AI readiness. So one of the #1 ways that the AI community has learned over the decades to help this process go forward is to create challenge problems. And the basic value of challenge problems, I'm going to walk you through it here. So if you had one team and they were solving one problem, let's say their win probability or success rate was, say, 20%. That's probably high, but let's just say it's 20%. And so if, like we have in the AI accelerators, we had 10 teams and they're working on 10 problems, so you would kind of expect sort of 2 solutions to those problems, which, that's great that we're getting 2 solutions, but there's a better way. There's a way that the AI community has developed over the several decades, and that is to take your 10 teams, have them work on 10 problems, and then identify key challenge problems where they get the data and example algorithms and all the various documentation together that then they can release to the community, and now you can get hundreds of teams working on those problems. And now the probability of being successful goes up dramatically. And this has been the kind of the go-to move of the AI community over the past several decades. And so the very first step in making a new problem, making it AI ready, is often creating a challenge problem. And these challenge problems often, these data sets often become the most valuable data set in any organization. They're well curated. They can be used to engage with others and collaborators, and they often become the bedrock of any tests because everyone understands them. And if there's issues, you can share them with technology suppliers and work through them. So creating challenge problems with appropriate data sets is often the best way to get started on the AI ready data path. So within the AI Accelerator, you know, we have our goal is to bring together world-class research for Department of the Air Force missions. We have a variety of missions we're working towards here. And as we can see here, the three foundational things that we're doing here are foundational AI research, education and training, and right in the middle there are the various challenge problems we're creating. And so we have a bunch of challenges right here, whether they be in weather, magnetic navigation, better management of data centers, radio frequency analysis, scheduling. That's what they call scheduling in the Air Force, is essentially do it on a puck board, and as well as assisting AIs in helping pilots in through something we call the Air Force Arcade. This is just about half of the challenges we have going on right now. You can see more on their website. You might notice there isn't a cyber challenge. That's because we're just kicking off our cyber project, and I want to just indulge you here in talking a little bit about that cyber project. So this cyber project, the goal is to create better networks through AI-enabled hierarchical connection science. So the way we look at the world in this problem space is that we look at it as a traffic matrix. And in this traffic matrices, the roads are sources and the destinations are columns. And because we're dealing with data from others, we make a real emphasis on working with anonymized data and having well-defined do not observe zones. There's certain places we're just going to not look with this data or make sure we don't even get that data. And then we want to sort of connect this up to understand what's going on in the data from a higher level. So we begin with our sort of foundational view, which is just the packet view of data, and we have an awful lot of packet level data. And then we're going to work all the way up this knowledge pyramid to looking at communities and trying to understand what they're doing. And so between that, we have various layers. We have flows, transactions, movements, and ultimately social media interactions. And we need to make sure that we propagate our do not observe zone. We don't want to accidentally leak information into the areas that we're not supposed to be looking at. And with this, we can then do sort of detailed within layer analysis as well as a cross layer analysis to develop the picture to help us understand what's going on with these networks and make them better. So that said, I've come to the end of my talk. Thank you very much. Again, AI software is very similar to other software with one big exception. Data continuously writes the AI software. AI data readiness is often 80% of AI effort, and pivoting to AI-ready data organization is really a prerequisite for AI success. And I encourage you to look at, learn about our challenges. And if you're really interested in the underlying mathematics of data, I encourage you to take a look at our book there. So thank you very much.